Right, so welcome to the first meeting of the Mornington Peninsula Astronomical Society for 2023, and welcome especially if you're a new member. Do please come up and say hello to any of our committee members, especially Nerida, who's not in the room at the moment. I think she's out there waving at the back with her coffee, and she'll say hello to you if you haven't already said hello online. My name's Peter, and since we haven't met here since November, there have been a few things to actually point out. Number one, the nearest black hole to the Earth was revised, and they've now found one only 1600 light years away. It was detected by the orbiting Gaia spacecraft, which is effectively like a stellar surveying spacecraft, and it's 10 times the mass of our Sun. Now, at 1600 light years, it's relatively close to us, which means it's considered in our backyard, but of no immediate threat from us. It's not currently feeding on anything, any nearby solar system, so it's been relatively hard to actually spot. We also had the NASA Artemis 1 mission, which swung around the moon and took a picture of the Earth on the way back. That one, of course, was the unmanned first mission. And by all accounts that went really well. We've also got an alert of a comet coming up. I probably won't say anything because Mark will probably have something to do in Sky for the month for that. No, you don't? Okay. Well, Comet 2022 E3, the name of it is given by the year and the fortnight of the month. So, sorry, the fortnight of the year. So E3 means that E is the fifth letter of the alphabet, so it's five in and then plus another 3 on the end. Now, it's on a 50,000 year orbit, so here's the solar system here with the Sun in the middle and the orbits of the planets around it. And the last time it would have come by would have been when the Neanderthals were around. Interestingly, they online they sort of exaggerated a little bit to say when it was last seen. Well, there's no guarantee it was seen by anybody 50,000 years ago, so they couldn't actually make that claim. Now, in the southern hemisphere, we should actually have it visible in the night sky from the 2nd of February onwards, but by visible, bear in mind it's only magnitude 11 at the moment, which you'll need a telescope to see at the best of times, and comets are notoriously bad at brightening to prediction, and it may not even get up to naked eye brightness at its very, very brightest for the southern hemisphere. So manage expectations a little bit there when this comet comes in the sky, that it's very unlikely to be a comet of the century. We have seen those before, but unlikely to in this particular case. Since we also last met, the NASA InSight rover, actually on the planet Mars, has come to the end of its days. And what you're seeing in this image, it's flickering away, is the before and after. So the nice bright one is the selfie it took of itself on the surface when it first landed in 2018. And in April 2022, that's what it looked like when it took its selfie again. And as you can see, it's somewhat dusty. And given that it's completely relying on its solar panels for its power, you can see why the thing had its batteries flattened down to such an extent that it won't recharge up again. So you can see that if you had even your solar panels on your house at home at that dusty, you're not going to get much power being generated at the best of times. So that's actually quite a good comparison there. Over on the right-hand side there was a meteorite that landed in 2013, just north of Port Augusta, and fairly recently the Monash University and Curtin University decided to try and find it, but they used a very different way. They knew it fell on the 31st of July because it was picked up by a US spy satellite. When it entered the atmosphere, it gave off the equivalent energy of about 200 odd tons of TNT going off, so it came in with a bit of a bang, and so they know the exact time that it actually came in. But what the university did was they actually went and looked at the Bureau of Meteorology's weather radar, and they actually used that to track the meteorite coming in. So they were able to actually work out the track by looking at the weather radar. You know, the one that you'll get if you go to the BOM website looking for whether rain is coming towards you. It's now can be used successfully to work out the track of incoming meteors. Then what they did was they took previous aerial surveys of their predicted landing site that had already had drones fly over them, taking aerial mapping, and they fed it into an artificial intelligence algorithm which had been trained up to look for meteorites on the ground. And it successfully managed to, it was believed to be about a 6-ton rock coming in from space, and they've managed to find 4 kilograms of it literally within 10 minutes of going in. The prediction was that accurate that the AI was able to actually successfully find those 4 kilos, and they reckon there'll be others other than the 44 pieces that were found as well, but they're hailing this as quite a success because it's a new technique that's used for finding new falls coming in from space. And the big news in the previous time was that break-even for nuclear fusion was done by the Lawrence Livermore National Ignition Facility in the USA. Now, a value of Q there, Q is defined as the ratio of the energy that you're getting out divided by the energy that you're putting in. So break even, when you get as much energy out as what you put in, has a value of Q of 1. They achieved 1.5. So in other words, they got a good 50% more energy out than what they actually put in with 192 infrared lasers. How it works is they basically have 192 lasers hitting a small pellet about the size of a peppercorn in size of deuterium and tritium. And what it does is they have to make it very, very accurately, and the lasers have to hit it from all sides simultaneously. And so they've got to get it exactly even and balanced. And when the lasers hit it, it causes the surface to basically explode and implode inwards at the same time. And the imploding inwards squashes the pellet to such a density and such a temperature that nuclear fusion occurs, at least until that pellet's fuel has been used up. And what they achieved was a value of Q of 1.5, but to actually make a commercial reactor, they estimate you need a Q of 10 for it to be viable. So they made a very, very important first step, given that they've been working on this for decades and decades. Even break-even has been very, very elusive up until now, so they did particularly well. Alright, tonight, so what we'll do is we'll go through, as usual, what has occurred since our last meeting and what's coming up. Then we'll throw over to Sky for the month with Mark. Then on to Chris, who's busily trying to tame the camera at the moment. And we'll have to swap positions there, Chris. Then we'll talk about the discovery of pulsars or neutron stars by Jocelyn Bell Burnell from Oxford University. This was actually awarded a Nobel Prize in physics and astronomy at the time, but she was not one of the recipients of that Nobel Prize. It went to her supervisor at the time and also to another astronomer as well, and it's always been a point of contention with that she was completely ignored, even though the discovery was actually hers. And then we'll look at the colour of noise at the end. So recent events, just after the last meeting we had a school out at Camp Mannion, and good conditions there, about 100 students coming. Then we had the massive Bentley Street Festival up in Bentley, and we had thousands and thousands turn up about that. And if you've had a look at the past Scorpius magazine that has come out since we last met, that was all covered in some detail there. On the same day we simultaneously went down to Rosebud for the Radio Fest. A couple of our members went down there and had a table for the people at the Ham Radio Fest. It's an annual event down there. We had a committee meeting which looked at not only the 2023 calendar but also having a member survey which has been out and about, and Chris has been looking after that. The letterbox is now up at the Briars, so Our official letterbox is now attached to the toilet on your way in and out, so it is actually up here now, rather than in a PO box in Frankston. And we're looking at updating the Society's flyer as well, and to redesigning on that because we've run out of flyers, so at the same time we give that a bit of a refresh. Then in December we had one public night left where we had just over 100 public turn up to hear Trevor give a talk before he disappeared on his cruises around the world on ships. Christmas dinner up here at the Briars was well attended, as it usually is for the annual roast. We had an impromptu public night for 3 of us in Frankston on the very last day on New Year's Eve, and we had a few people turn up for that one, but not too many, given that it wasn't really advertised very widely. In January we've had 3 public nights so far, on the first Friday, second Friday and the first Saturday. So Catherine and Dave gave the talk on the first 2 nights, and I gave the talk on the third night. Unfortunately, so far this year we've had no cloud when it came to the important part of the evening of going out to the telescopes. So all being well for the upcoming ones. So coming soon, we'll probably have a bit of a working bee this Saturday at the Briars, if there's anything left to be done. I don't know, Phil, if there was anything?
There's plenty.
There's plenty, okay, 4 PM as usual. Committee meeting will be next Wednesday by Zoom as usual. Then our next public stargazing night is the night after Australia Day, so we will be up here. We're anticipating about 85, and Guido should be back at that stage from his travels in the Grampians. Then the Saturday afterwards, Eden White will be here with the Cosmology Interest Group here at the Briars at 2 o'clock. Those are interested in cosmology topics. 3rd of February, the next public night, is Manfred giving the talk, and both of these are actually booking quite pretty close to full, I would think, by now. And our next meeting here is on the 15th of February. Now, looking a little bit further afield, the Telescope Learning Day, which is something that we've been running in more recent times twice a year, so this is the first one for this year. We'll be here at the Briars from 4 o'clock until 10 o'clock at night on the 25th of February, which is a Saturday. But you do have to actually book to come to that one because it's fairly limited, and particularly for newcomers that know nothing about telescopes and are interested in telescopes, whether for themselves now or in the future, then that's a very good one to come to. It will also be open up to the public to come as well, so any members that are interested in coming along to that would be advised to book early. Then we've got on the 4th of March, which is a Saturday, also here at the Briars, another collaboration with the Southern Peninsula Concert Band, which will be a musical trivia night, and you also have to book for that one as well, which will start at 6 PM. And that will be an outdoors thing, it won't be indoors. If for some reason it's pouring with rain on the night, then the evening will be cooled off and rescheduled to another night. So it's not all entirely indoors. Like the last significant concert that we had with them was actually held in the room here, and we had a lot of people, but that was all pre-COVID days. So this one will be an outdoorsy thing. And on the 13th of March we should be down at Somerville for the Somerville Family Fun Day, which I think is a Sunday from memory, which will be all day, but no booking is needed for that one.
Hi everyone, welcome to the first guide for the month for January 2023. For the new members, generally what I do in this session is I let you know what's astronomically interesting in the next month, worth having a look at, trying to get your telescope aimed at and that sort of stuff. So, any further waffling, we'll move straight on. During January and February, I'll go part way into February because the next meeting when I do the next one is halfway into February. So the moon, we have a new moon on the 22nd of the 1st, so hopefully nice dark skies, and if I see correctly we had 0 cloud for all PBNs, something's gone wrong. Okay, so the next full moon is on the 6th of the 2nd. and it'll be just after apogee when the moon is at its furthest point. So the next full moon is going to be a smaller one, all right, rather than a really big one. Other things to look for already occurred. Mercury in inferior conjunction, essentially meaning it's between us and the Sun. Slightly different, not exactly between us and the Sun, or we've got a transit. Those are fairly rare, so we didn't get a transit this time, and probably in the next 10 days or so, if you want to have a look at Mercury, you're going to have to get up early in the morning and have a look. It'll be a morning object for probably about 2 months. Comet Pan-STARRS, there's 2 Comet Pan-STARRS. K2 is in Parvo, which for those of you, the next slide will show you where Parvo is. It's very deep south, near the South Pole. So you'll need a fairly good, not the South Pole, South Celestial Pole. So you'll need a very good southern horizon before you'll actually be able to maybe hunt it down. But as Peter said, a lot of these comets are around 11th magnitude, so they're definitely telescope objects. On the 22nd of the 1st, when it's a new moon, the moon's at perigee, so we're going to have a super new moon. It'll be worth looking at, won't it? We won't see anything, so missed out there, haven't we? On the 22nd of the 1st also, Saturn will be about half a degree northeast of Venus. Now these 2 planets are over in the very much in the twilight zone at the moment. Venus is quite visible, Saturn not so much. Half a degree, if you hold your arm at full length, that's the width of your thumb. It's about half a degree. So the width of your thumb apart. So worth having a look for anyway, just before it gets really dark over there. Comet K1 Pan-STARRS is in Sagittarius, which sits fairly close to a globular cluster in Sagittarius, which essentially makes it a morning object, AM object. So if you want to see that, you're going to have to get up basically after the witching hour. On the 30th of the 1st, Mercury will be at its greatest elongation west, which is as high as it gets above the horizon, or away from the Sun if you like. Apparently this time it will be a fair distance above the horizon, so if you are an early riser and you want to have a little look at Mercury, apparently it's going to be in a reasonably good spot to view, assuming you have a fairly good eastern horizon. Ceres, now I mentioned Ceres because it is the biggest, brightest star of the asteroid belt, 0.05 degree northwest of NGC 4694, which is a galaxy in Virgo, 3 AM. Okay, so a lot of this stuff's forming at the moment. But if you really want to get up and try and find an asteroid, that's one to have a go at, being the biggest of them. From the 8th to the 2nd is the maximum for the Centaurus meteor shower, beginning on the 28th of this month and winding up around about the 21st of the 2nd. Other than that, there's no real meteor showers visible in the southern hemisphere at the moment. There is one occurring a bit in the north. And Comet Wild 2, I do mention more about comets later on, 1.5 degrees north of IC 4592. IC is your index catalogue of astronomical items. For those with go-to scopes, you should have the option to select an IC object in there. And it's in Scorpio, which is also an AM target at the moment. So the sky for January night sky looking towards the south, that's down that way, South Celestial Pole. You'll notice the Eta Carina Nebula now getting a little bit higher and not too bad. Parvo, where you'll find that comet, is down here. The way to find that is you've got your Alpha and Beta Centauri here. Next to that you've got Triangulum Australis, and these 3 stars here are quite easy to find. And it points straight at Parvo. So if you want to go comet hunting, that's the best way to try and find it. Other things up at the moment, the Tarantula Nebula, which is in the Large Magellanic Cloud, and a bit of a favourite object for people to photograph, that sort of stuff, because you can't really see it with your eye. 47 Tucana down here, globular cluster, right next to the small Magellanic Cloud in the Toucan. Quite an easy one to find, not far from the South Celestial Pole. The other one being Omega Centauri, which is the biggest one in the sky. Omega Centauri at the moment is probably still a little bit close to the horizon, but for those with a good southern view, you've got a reasonable chance of finding it at the moment. And the last one I'll mention here is the Ghost of Jupiter. Now, the Ghost of Jupiter up here, if you look at your Southern Cross and that sort of stuff, if you look at it through a telescope, it literally does look like a ghost of Jupiter. What it actually is a planetary nebula, or what's known as a planetary nebula. Essentially, it's a sun that has destroyed itself, essentially the way they think ours will go, and it sheds its outer layer. And that outer layer is visible in the scope. It looks like a nebula, but the shape of it makes it look like Jupiter, the planet Jupiter. It's about the same size and looks the same, except it's hazy. So that's a good one to try and get, and you'll probably find if you look up the NGC of it, go-to scopes will get it fairly easy. There's not a lot out there. I mean, not far from Regulus in Leo, which is a bright one in Leo there. So if you want a star crawl, you can have a go, or you use your go-to scopes. Looking to the north, it's, you've got the Milky Way virtually stretching right across, and you'll notice the angle of the ecliptic plane at the moment. It's laying right over on its side. The reason for that is because when we get to our night, at the moment, the South Pole is tilted towards the sun, or is angled towards the sun. And so when we get to our night time, we're actually on the bottom of the planet. So we're sort of looking down below the planet. But as the ecliptic plane is that way, and we're standing down here, we're looking at it, it appears to be laying over. Is that clear? It's a slightly difficult concept, I know. The main reason I talk about it is because that is the plane on which the planets and pretty much everything that cycles through the sky goes along that plane, with the exception of stars elsewhere. Alright, obvious one there is M42, the Orion Nebula. Very good target for new astronomers. It's the sword of Orion, it's quite easy to find, and looks pretty good in even a modest sized telescope. So the planets, Mercury, as I said, gone through inferior conjunction between us and the Sun. We turn to the morning sky as the month progresses, reaching its maximum elongation on the 30th of the 1st. But once again, if you want to see Mercury, you're going to have to get up just before sunrise. Venus, on the other hand, is not as fast as Mercury. Mercury does one orbit in 88 days, so a quarter of its orbit in 22 days. Venus is a little bit more pedestrian. It's currently in the western evening sky. It is getting higher. About this time now, it's probably just a nice distance above the horizon. It's still in the twilight, but it's quite bright. And the beauty of looking at Venus while it's still in the twilight area is you haven't got that high level of contrast. Very bright planet because of the clouds, it reflects a lot of sunlight. And when you've got a black sky behind it, it can tend to flare in your eyepiece of your telescope. But if you actually look at it while it's in the twilight area, there's still a bit of blue sky behind it and that sort of stuff, it seems to mute it down enough that you actually get a better view. And it will show presence and give you, like the moon does, and that's because it's closer to the sun than what we are. Mercury does the same, but being a much smaller object, not quite as obvious. Okay, as I said, on 22nd and 23rd, moves within 1 degree of Saturn, so fairly close, 2 thumb widths. You've got Saturn and Venus next to each other. they're on the horizon on the 23rd. They'll be joined by a 2-day-old moon. So you'll have a sliver of moon, Venus and Saturn, sorry. Earth, as I said, South Pole angled towards the Sun, giving us the Southern Hemisphere summer. And on the 5th of the 1st, so a little while ago now, not that long ago, Earth was at perihelion, in other words our closest approach to the Sun, which tends to be why it happens every time we have summer, which is why our summer tends to be a little bit more brutal than the Northern Hemisphere. Not this one was just rain, but normally that's the way it is. The outer planets, Mars is now past opposition. That's still at a pretty good place to view. It's still a fairly reasonable size, so this month and then maybe the next couple of months is the time to view it before it'll disappear again for 2 years. So it's just the way our orbits work. We get to see Mars in the evening sky every 2 years. Obviously, if you've got enough eyepiece or power on your telescope, you can look for the polar cap. The North Polar cap tends to be a reasonable size, and the dark markings on the planet's surface. It's at the moment, it's in Taurus. Don't confuse it with Aldebaran, because Aldebaran is the red giant, so they're both reddish. Mars is the brightest of the two. Jupiter, still fairly high, it's in Pisces, so still fairly good position to view it, and its sheer size and relative proximity to us makes it a very good object for particularly newer astronomers to go for. You're obviously looking for the moons, and the other thing too, if you've got enough power on your telescope, is your moon transits across it. You're looking at, as the moon goes across the front of it, sometimes it'll cast a shadow on the planet. Quite an interesting thing to look at. Saturn now getting very low in the western sky. We're probably about to lose Saturn. It's not very high at all. So maybe this month, the rest of this month is about your last chance to see Saturn, and if you're prepared to get up in the morning in a few months' time once it becomes an AM object. Uranus can be found in Aries. At the moment they're all sort of tracking in one part of the sky, so we'll ultimately lose the planets for most of the year until they start to reappear around about July, August. But Uranus is in that group there, due north in the ecliptic around 7 PM, so it's past opposition, and it's almost a naked eye object. It's about 5.5, 6 magnitude. So probably you need kids' eyes to have a chance of seeing it with the naked eye. Other than that, it's a telescope object. And Neptune is very close to Jupiter. It's just a little ahead of it in terms of progressing towards the western sky, but it's still a difficult one to find purely because it's about the same brightness as the stars around it. But worth having a go at. Appearance of the planets, Mercury, mostly black because it has its back to us. It's just passed through inferior conjunction. When it gets to its greatest elongation west, you should see it as a crescent. It's probably the best time to see it as a partial planet, as a crescent, because it's almost chopped in half. Venus, on the other hand, popping up in the western sky now. It travels faster than us, so it's actually coming around between us, and that sort of stuff. As it gets closer, we'll start to see more black, but the whole planet gets much bigger, so you will definitely see the various phases or crescents of Venus. Mars at this stage is about the same size as Venus, in the same scope, and still in a pretty good position. Definitely red, you can see the red with the naked eye, and that sort of stuff. So through a telescope, as I said, you'd be looking for a nice big patch of white on the northern hemisphere there, which is its polar cap. It does have one on the south, but it tends to be a lot smaller. Saturn, still putting on a pretty good display with its rings, but you notice it's a lot smaller than it was, and it is starting to get into the twilight, sun's twilight now, so it's getting a little bit harder to spot. Jupiter, still in a very good position, still very big and bright in the telescope. You're obviously looking for these bands. If you're lucky, you might see the red spot. which apparently over the last couple of years has shrunk. And I was looking at something, or reading something on it the other day. Apparently, it actually turns the opposite direction to all the other. It's an anticyclone or something, and so it's effectively a hole in the planet. Well, I suspect it's a hole in the planet. So what you're seeing with the colour is stuff more deeper in the planet. And Uranus, even fairly close up, it's reasonably featureless, so don't expect to see too much stuff on Uranus. And Neptune, if you can see a blue dot, you're doing pretty well. Other stuff, comets. Fortunately, there's no meteor showers this month, but there's plenty of comets. You've got Pan-STARRS K2, currently at 8th magnitude, so definitely a telescope object. And it's the one that's in Parvo, that southern constellation, and it is moving more towards the eastern horizon at the moment. There was the one, it got to about 6th magnitude, which is pretty good for a comet, but yeah, it's on its way out now. P2 is the one in Sagittarius. It's at 12th magnitude, so very faint, and definitely need a telescope to see it. And basically, as I said there, it may not be worth getting out of bed for. Comet Wild 2 in Libra, about 10th magnitude, and it's rising in the eastern sky around about midnight. So not too bad if you want to have a bit of a look at it. Beauty is Libra is not a particularly bright constellation, so the comet hopefully is easier to spot. And the last one, Comet ZTF. That's certainly a funny name. I don't know who that was that spotted. It's only visible briefly in the northeastern sky just before sunrise. And so probably wait till next month. Apparently it's going to be slightly better to view next month. So we'll put it up there for it. Upcoming events, the barbecue and the working bee on Saturday the 21st, starting at 4 p.m. It's a good way for particularly newer members to get to know other existing members and that sort of stuff. It's a nice social occasion. Different people will be burning the sausages this time, so yeah, come and see how well we do it as opposed to Jamie. We've still got the summer PBNs coming up Friday the 27th of January, 8 p.m. and Friday the 3rd of February. Once again, members are able to come along, and you don't have to know a heap. You can stand around, you can learn from the members who do know a little bit. It's another great opportunity to get to know people and get to be known. And as I said, you don't have to be a know-all, that sort of stuff, but just generally be around the place and help out where you can. Tonight's information was provided by Astronomy 2023, Wallace Stores in Northfield, and I do know Simon has still got a handful of them available to sell to members, anyone who wants to be able to look all this stuff up themselves. Any questions? Any easy questions? Okay, thank you.
Okay, hi everyone, welcome to Astro Mofo, edition number 1. Edition before was introduction, so this is a first edition. Now this, as you might know, is the challenge that we set to members to get out and photograph a designated target every month. The last one was the Large Magellanic Cloud, so people were out photographing it, submitting their photos to the socials or emailing them in, and now we come to review them and set our next target. So let's go. Okay, now this challenge, the Large Magellanic Cloud, was announced at the November meeting, so we had a couple of months to photograph our target. Congratulations to everyone who accepted the challenge, and we've got about 10 members who submitted photos. So we've got Ben Claringbold, Chris Black, Chris Kostokanellis, David Rolfe, Guido Tack, Jamie Pole, Nerida Langcake, Nick Axeris, Rob Clark and Russell Smith, who provided some photographs for us. And it was good to see there was a wide range of equipment, anything from smartphones to large telescopes with filters and astronomical cameras. So it was pretty good to see. Before we go on, we just want to say congratulations to Nick Axeris, who won the second prize for this image in the 2022 Optolong Deep Sky Astrophotography competition. Nick posted this photo on our Facebook page in November last year of the Tarantula Nebula, which he shot with his 130mm refractor, his ZWO 294MC Pro camera and his Optolong L-Extreme filter, which made him eligible for this competition. So this was submitted by members from all over the world. It's not just an Australian competition, and Nick was recognised for this image, so congratulations, Nick. This image doesn't qualify for AstroMofo though, because he posted it a couple of days early before I announced the target, so that doesn't qualify. We've got another image from Nick though, which does. Okay, we've got this time lapse to start off with by Jamie, which was done here at the Briars. I think we'd set up on the 27th of December, hoping to get some aurora. But I'll just play this. It gives you an idea of, we've got the Large Magellanic Cloud right up the top of the screen there, and it gives you a bit of an idea of how it moves through the sky during the course of the night. So you can see it just making a bit of an arc, a bit of a circle as the night goes on around the south celestial pole there. I think we can also see a bit of a hint of aurora, a bit of pink coming up just above the southern horizon there. So, and then you have also the Milky Way, so we get to see its position, and also the Small Magellanic Cloud just off that. We did get a bunch of tarantula shots. So this one was by Ben Claringbold with his setup, which many of you might have seen. Ben always sets it up at the public nights with his camera and his telescope. So that was taken by him with his ASI camera. No filters on this one, so this is just colour visible light with a few 25-300 second exposures. This one was by Chris Black, which is a wider field image, getting pretty much the whole Magellanic Cloud in there. You can see the tarantula, the main body of the cloud, and there's a few little smaller nebulas and globules that you can see scattered around there as well. So that was a nice one by Chris Black, taken with his red cat. These were by me. We've got NGC 1763, which is a nebula just sort of on the opposite end of the Magellanic Cloud from where the tarantula is. And it's another star-forming region with quite an active star-forming region in the LMC over there. And the other one is a wider shot, again taken through my telescope at about 400mm focal length with the reducer on it. Then we also have this one here by Dave Rolfe, shot with a monochrome camera and his 130mm refractor. So he's got hydrogen alpha, O3 and S2 filters on it, and combined those to give us this beautiful shot of the tarantula as well. And we've got this one here, these photos here by Guido as well. So this one here you may have seen on our last newsletter. It was featured on that, and that's with his Skywatcher, his Newtonian reflector, 250mm reflector, and his ASI 294 colour camera with the L-Extreme filter, Optolong filter. So L-Extreme filters are a dual band filter which filter through hydrogen alpha and O3 light, and just really highlight the nebulas. The other one on the right there is with his 700D camera at 100mm focal length on a tracking mount. So he's got an astrophotography camera on one of them and just a standard camera with a standard lens on the other one. And this one is by Nerida, taken at the Snake Valley Astrocam with her smartphone, Note 20 Ultra. So it's a single shot there. You can see the Large Magellanic Cloud just at the top of the image there. Better than yours. This one here is by Nick Axeris. So again, pretty much the same setup as his other shot that we saw earlier with his 130mm refractor and his 294 MC Pro camera. So he's got about 8.5 hours of exposure on this object and then processed it to give us this. So we're seeing a few different objects here. We've got NGC 2020, which is the little blue donut, and that's home to a Wolf-Rayet star, which are supermassive stars which are blowing off their outer atmosphere. They're some of the largest stars that we know, and they're rare. We think that there's only around about 2,000 of them, I think, scattered around the Milky Way. That one there is in the LMC, but they are massive stars that are going through a phase where they're blowing off their outer atmosphere, and that is home to one of them. Then also we've got NGC 2029, which is the light blue nebula just on the left of the screen there, and what else we've got? 1968 in the centre. I won't say what that looks like. We also have a large 6x4 panel mosaic here, which is a work in progress by Rob Clark. So he's shooting this with his 250mm Newtonian and the 294 MC Pro camera. So it's still a work in progress, but it's a massive image, and it's just panel by panel him shooting it individual frame with his Newtonian and stitching it all together. So love to see what that looks like when that's done. And another one by Rob, come on, is this one here of NGC 2020, again with that donut-shaped nebula home to that Wolf-Rayet star. He shot this one with Barlow and the dual band filter as well. And finally we've got this one here by Russell Smith, which is a hydrogen alpha photo with a hydrogen alpha filter and a monochrome camera with a 130mm refractor. Everyone's got these 130mm refractors. We've got to get one of them. And a monochrome camera. So that really shows, highlights where the hydrogen alpha in these things is coming from and what's the glowing gas that makes up a large part of these nebulas. Okay, our next target is the Orion constellation. So Orion, Mark pointed it out in his talk earlier. It's in the north, big, can't really miss it. So there's a lot of target options to shoot on this, and you know, quite a few different ways. You can go, we'll try and get the entire constellation, and you probably need to shoot it with, if you've got a full frame camera, about a 70 or 80mm lens to get the whole Orion in there. And if you're really good, you'd be able to get the nebulas and Barnard's Loop, which is a growing red ring of gas around just to the right of the constellation as we're looking at it, and that usually comes out if you take enough photos and stack them up. We can go for individual stars. You can photograph Betelgeuse, for example, or Rigel, or Alnitak, or something like that. And then there's also the nebulas, which we know, M48 and the Horsehead, the Flame Nebula, the Running Man. And also there's another one as well, if you want a bit of a challenge, M78, which is, how do I point it? Okay, about here. There's a nebula there called M78, which is a little bit smaller and fainter, so if you've got a bigger telescope, you might have a crack at that one there. There's a couple of clusters worth trying to shoot. There's a few around Orion's head, and there's also, if you've got a bit of magnification, you can try and get the trapezium cluster at the middle of the Great Orion Nebula, just over there in Orion's Sword. Okay, so as usual, submit your photos to MPAS Facebook page, eScorpius, or email them to me. And if you like, when you do that, submit a bit of information about your photo, about your equipment, and also anything that interests you about the object that you're photographing, anything that you find interesting or want to share about it, a bit of information, and yeah, we'll put them up. Now, I'll be at the next members barbecue. If anybody wants a hand or a bit of guidance, I'll do what I can do, but there's more knowledgeable members than me, and we'll try to get you going. So, happy snapping.
Thanks, Chris.
The main video tonight is going to be this one. It goes for about an hour and a quarter, so if you want a tea break at any time during it, just quietly get up and go out the back and help yourself, and feel free to wander back in with your tea and coffee during that time, given that it's about 10 to 9 at the moment. This is a picture shown there from 1968 from the Moriarty Radio Observatory in the UK, Oxford University, of a very young Jocelyn Bell Burnell when she came across pulsars for the very first time, and went on to discover several others as well. Now, this is a public lecture that was given a couple of years ago in Ontario, and it's given by her. She's somewhat older, given that this was 50 odd years ago, but nevertheless still bright as a tack.
And a very warm hello to all of you who've joined us on this really special occasion. We have an amazing full house here at Perimeter, and of course many people around the world online. We're absolutely thrilled to have Jocelyn Bell Burnell as tonight's guest lecturer, a great scientist and a wonderful person. She has served in many prominent roles as president of the Institute of Physics, of the Royal Astronomical Society, and of the Royal Society of Edinburgh, and she's won many awards. This year, she was awarded one of the biggest cash prizes in science, the Special Breakthrough Prize in Fundamental Physics, for her discovery of pulsars in 1967. And characteristically, she has donated the entire award to support physics PhD studentships for people from underrepresented groups. It is a great pleasure to be able to celebrate that award with her tonight. Before I welcome Jocelyn to the stage, I want to acknowledge another very special individual with us here tonight. The co-recipient of the 2018 Nobel Prize in Physics, Donna Strickland of the University of Waterloo. How fortunate we are to have these two extraordinary women with us tonight. Donna and Jocelyn, we have a little surprise for you. Over the past year, Perimeter has celebrated pioneering women of physics by creating a series of free posters called Forces of Nature, which both of you are. These posters are already hanging in classrooms and homes around the world. To commemorate the incredible things you two have done, we've included you among the forces of nature. I should emphasize these posters are all free to download from insidetheperimeter.ca. Now, it is my great pleasure and honor to give the stage to Jocelyn Bell Burnell, who will share with you her incredible story.
Thank you very much. So thank you to all of you for this wonderful welcome. Thank you to Perimeter for the opportunity to visit. And thank you also to BMO for funding Women in Science. I'm going to talk a little bit tonight about the stars that I discovered when I was a grad student. It is 50 years ago. I suspect the memory has been sanitized slightly in the interim, but I hope you still find it a good story. So I'm going to say a little bit about what radio astronomy is. I will have to say a little bit about quasars, because that's what I was meant to be doing. I'm going to say a bit about being in Cambridge, United Kingdom, and the discovery of pulsars, and then also a bit about what pulsars are. I'm starting with material that maybe you all know. I'm going to just remind you about the family of light. Technical name, the electromagnetic spectrum. You will have seen a rainbow, I'm sure, with the light colours split up into its different wavelengths. It's right in the centre of this diagram. There's a lot of other radiations that are of the same family as light, which our eyes don't see, like all of this and all to the left. So we are a bit limited, actually. There's a lot else that we might have been able to see had our eyes been different, but we can't. You'll have heard of some of these. If we come out the violet end of the spectrum, we come to ultraviolet. Ultraviolet disco lamps, luminette fluorescence, things like that. It's also ultraviolet in sunlight that causes sunburn. Go beyond the ultraviolet, we come to X-rays. It's alarming how many of us have had X-rays, but the X-rays that we've had have been generated by human beings. Stars and galaxies also naturally generate X-rays, and astronomers study those. And beyond X-rays are gamma rays. Gamma rays sometimes used in cancer treatments, for sterilizing food, for sterilizing hospital instruments. And if we go out the other way from the little rainbow we can see, we come to infrared, beyond the red, as in infrared lamps, infrared heaters, coming on into what some people would define as radio, millimeter wave stuff, radar, microwave ovens, microwave links, in through the television band to the radio bands. And stars and galaxies we now know radiate right across the spectrum. Not all of them across all of it, but at each bit you can pick up various stars and galaxies. This is a photograph of the iconic British radio telescope at Jodrell Bank. Photograph taken near sunset, as you can see by the nice red sun. The telescope is looking up to the top left. The dish collects the radio waves, focuses them up here, where there is a detector to pick up the radio waves, and then there's a cable will come all the way down and into the laboratory in the building where there'll be recording equipment. We don't usually listen to radio telescopes because we need some kind of hard record. So it comes out on paper chart, if you're as old as I am, or computer records these days. Radio astronomy was developed following World War II. A number of people had worked in radar, developing radar as a wartime instrument. And at the end of the war, those people quite often, at least in this country and in the UK, managed to acquire some of the radar equipment, take them back to their universities and start radio astronomy observing. So they no longer transmitted the way radar did, just received. And in Britain, actually, we had a number of German radar dishes which were requisitioned. The people who worked on radar were inevitably known as boffins. And unfortunately, the name stuck for quite a long time. But when people turned these radio receiving dishes to the sky, they found a wealth of radio emitting things up there amongst the stars and galaxies. And a lot of excitement and a lot of interest in ascertaining what exactly they were. One of the big puzzles was some of the brightest of those sources. Things that have become quasars because they looked quasi-stellar, like stars, but not properly stars. They were a big puzzle for quite a while, and then in 1963, Martin Schmidt, a Dutchman working in the United States, finally cracked it. The spectrum, the optical spectrum that they were picking up for these quasars, could be explained if you gave it an enormous shift to the red end of the spectrum, which in turn implied these things were very, very distant. So how can they be so very bright if they're very, very distant? Well, actually, both statements are true. They were very, very bright in radio waves, and they are very, very distant. So quasars rapidly became a very intriguing topic. A couple of years later, I moved into radio astronomy, having done my first degree, and the quasars were a very hot topic. Slight digression to explain the next little bit. You've probably already noticed my funny accent. Map of the British Isles. I started life in Northern Ireland. I went and had a lot of my secondary education in York. And I went and did my bachelor's degree in Scotland in the University of Glasgow. And then, rather to my surprise, I found myself in the deep south, in Cambridge. Well, you can find all that on a regular map, but you won't find that. Of course, Canada, being a properly egalitarian country, doesn't have anything like this, does it? But when I turned up here, I really felt like some freak from outer space or somewhere like that. They were all terribly confident, terribly bright, quite keen to let you know it. And I kind of quailed. We now have a name for this. I wonder how many people in this room have heard of imposter syndrome. A few, right, that's helpful, good. Imposter syndrome is when somebody from the sticks turns up at a posh place. It might be to study, it might be a new job, and they suddenly realize, ooh, they're all very clever here. I'm not. They've made a mistake admitting me. They're going to discover their mistake and they're going to throw me out. And in a bad case, and I'm at University of Oxford, and we sometimes get this, in a bad case, the student will say, I'd better leave before they throw me out. And they're gone after a week of term. And it's quite contagious. They sometimes take one or two others with them. I recognized now that I was suffering from imposter syndrome. I came from this north and west uncouth part of the country, turned up in this very suave Cambridge. And I thought, they're all terribly bright here. They've made a mistake. They're going to discover their mistake. But I'm a bit of a fighter, so I said, I will work my very hardest until they throw me out, so that when they throw me out, I won't have a guilty conscience. I'll know I've done my best and I just wasn't bright enough for Cambridge. Zeldovich, one of the new fellowships here is named after Zeldovich. This wonderful quote, I don't think it was said of Cambridge, but it could be. Frequently in error, but never in doubt. I'm told he said it of cosmologists, but of course there aren't any of them here, are there? My discomfort increased slightly when, first day of this formal PhD program, the graduate students in radio astronomy got given each a set of tools. Well, that's not quite true. There were some funny characters called theoreticians. They didn't get given a set of tools, but the rest of us did. And these are not microelectronics tools. These are heavy-duty wire working tools. And I still have mine, and this is them. I was to spend the next 2 years helping build a radio telescope, a homemade radio telescope at the Radio Astronomy Observatory a few miles outside Cambridge. I was given responsibility for all the plugs and connectors. I was spared quite a bit of the sledgehammering, but by the end of my PhD, I could swing one of those sledgehammers. Not the sort of skill you normally expect to get during a PhD. This is near the end of the project and shows you the kind of working conditions we have. The technician who worked with me, Don, and myself. We have some very expensive low-loss cable. You can't coil it up and take it indoors. So to put the plugs on the two ends, I was provided with some little shelters. And I sat inside these little huts and put the plugs on each end of the cable. And here we're checking the impedance using a slotted waveguide. What you don't see is that it's about 300, 400 meters to the nearest power socket. It's literally working in the field. And one of the things I discovered is it's very hard to solder in the field because the wind cools the soldering iron. It's some complications. The telescope was a huge area, covered the equivalent of 57 tennis courts. It was fairly cheap as things went in those days. And as I say, there was a group of us spent 2 years building it. This is the finished product. It looks like a homemade radio telescope. It was a homemade radio telescope. There's over 2,000 antennae there. Maybe some of you will recognize the nice bluey green of oxidized copper. Several tons of copper in it, all in the form of wire, and about 190 kilometers of wire and cable in total. For those who want something slightly more technical, it worked at a wavelength of 81.5 megahertz. That's a big wavelength, 3.5 meters. 2,000 odd dipoles, over 1,000 wooden posts. They're really important because you've got to keep all this stuff out of the wet grass. Wet grass is an electrical short. So if you don't have all your stuff well clear of the wet grass, your signal runs to ground. As a student in Glasgow, I had used transistors as part of my final year project. Was slightly surprised when I turned up in Cambridge to find they used valves still. So I said, why don't you use transistors? Whoa, noisy things. Whoa, unreliable. We use valves. They ultimately changed, but they were pretty cautious. Now, my job was to find more quasars. And my thesis advisor, Tony Hewish, had recognized that there was a very neat way to do this. So I'll now try and explain this phenomenon. It's called interplanetary scintillation. Scintillation means twinkling, and interplanetary means between the sun and the planets within the solar system. So we have a quasar. I've marked it on my graph as here, but actually it's way, way up at the ceiling, a long, long way away. And the radio waves from the quasar come down towards the radio telescope here on the Earth. And to get from there to us, they have to come through the space between the sun and the planets. And that space is not empty. There's a wind blowing out of the sun, an ionized wind. And that ionized wind is not perfectly smooth. There are some clumps or clouds in it with slightly greater electron density. And these clumps or clouds cause the radio wave from a compact object to be spread out. And because this ionized medium is blowing out from the sun with the solar wind, these clouds, so to speak, blow past. And what an observer sees is a fluctuating signal from the distant quasar. You may not be able to read it, but that bar is a time scale of about 1 second. Ordinary radio sources, which aren't quasars, are much broader. Remember that quasar is quasi-stellar, so it's pretty compact. A broader radio source, you see through several of these clumps at any one time. And so the clumps blowing past, there's minimal change in brightness. But a compact object will show quite extreme changes in brightness. So, my thesis advisor, Tony, argued, all we need to do is to survey the sky and look for objects that fluctuate in brightness like this, and those are the quasars. And that was the project. But first, you had to build your radio telescope. An analogy, it's not perfect analogy, so apologies to the physicist. This is a picture of ripples on the floor of a swimming pool. And as the wind blows, this pattern of light and dark moves across. So if you imagine yourself lying briefly on the floor of the swimming pool and looking up, you see these bright and dark things go by. And it's a bit like the twinkling we observed for the compact quasars. I've probably said most of this. The one thing I need to stress is if you're going to see this rapid fluctuation, you need to be taking short exposures. You need to have a short time constant, a short integration time. And we used one of 1/10 of a second. Spent the first 2 years building the telescope, and at the end of those 2 years when it was finished, the rest of the group that had been involved in construction moved on to other projects, and I was left to get the telescope working, debug it, and use it for about 6 months. So I did that, and I found about 180 more quasars, taking the number of known quasars from 20 to 200. So we had a good sample at the end of it. And in fact, my thesis had to be on that, because Tony said it was too late to change the title. I put the pulsars in an appendix, and it's probably the most read appendix of anybody's thesis. Sorry. So, University of Cambridge at that time had one computer. It had memory less than your laptop, and it took up a very big room. It was full of valves. Very few academics got time on that little computer. Martin Ryle, who headed the group, did, because he was making maps of the radio sky using Fourier techniques. And doing Fourier inversion by hand is quite hard work. So he had time. Every other academic in radio astronomy had grad students instead of access to the computer. And our data came out on long rolls of paper chart, and this is a piece of it. We got 30 meters every day of this paper chart. It took us 4 days to complete the scan of the sky. So one sky scan was 120 meters of chart. And I operated the telescope for 6 months, accumulating over 5 kilometers of chart paper. And I can assure you I've looked at every fraction of a centimeter of that, and some of it twice over. Got used to identifying quasars, got used to identifying human-produced interference. These days, radio interference would be mobile phones, maybe microwave ovens, aircraft altimeters. In those days, it was badly suppressed stars, sparking thermostats, sparking power lines, things like that. And because we have this enormous radio telescope, it picks up interference really, really well. This is a sample, carefully selected, of the chart. It's a stretch about real, well, on this screen it's about real size. And in Tony's handwriting, he's identified the first sighting of a pulsar and some low-level interference. So this is a distant, badly suppressed car or sparking thermostat. And people near the front can probably see that the two look slightly different. This one, the spikes go up and down, and you can see chart paper between the spikes. On this one, the spikes go largely upwards, and there are places where they're really packed solid. If we've any students in the audience, what you're doing when you make that kind of comparison is a kind of Fourier analysis. You're commenting on the amplitudes of the waves that make up these signals, and you're commenting on the frequencies. You know, here we can see space between the spikes, low frequency. Here we can't. I did a physics degree, and I'd argue that maybe anybody who's done a physics degree will have had the same experience that I'm about to describe, unless they're terribly bright, because it involves bits of physics that you're meant to be learning as a student that you don't properly understand yet. And so when you have an exam, you have to learn it off parrot fashion. And there were bits of physics, not too many, but there were some bits of physics that as an undergraduate I had to learn parrot fashion. And those bits of physics really bugged me. I kept saying to myself, I must find the time and go back to sort that out. The problems that I didn't understand lodged in my brain. I think the same thing happened here. At some subconscious level, this bit of signal that I couldn't explain, even though it's only about 5 millimeters long, it lodged in the back of my brain, unknown to me. But after it had come a few times, my brain said, you've seen something like this before, haven't you? You've seen it from this bit of sky, haven't you? And then it's easy. We survey the sky in strips. Well, we point the telescope at one level and we let the Earth turn it. So we get a strip of sky, and another strip of sky, and another strip of sky. And I keep these rolls of chart paper filed in shoeboxes, labelled with the strip of sky. So having suspected that I've seen this before, this was declination 23 beam, I go find the box that says declination 23, pull out, get the charts out, spread them out. You need lots of floor when you've got this amount of chart paper, and line up the different charts so as they're all properly lined up. So, here's this one. Wasn't there that time, didn't see it that time, didn't show that time. Oh, it might have been there. It's a bit faint, but it might have been there. No. Yeah, that's one of the ones I logged before with a question mark. And so's that one. And you know, they all line up. They're keeping their place amongst the stars. They've got the same right ascension is the technical term. Now, you probably have noticed that there are different constellations in the night sky and in the daytime sky. Sorry, in the summertime sky. You don't see many constellations in the daytime sky. And the reason you've got different constellations in the winter and summer skies is because the stars do not go round in 24 hours. The stars go round in 23 hours, 56 minutes. And that 4-minute difference accumulates and makes a difference. This thing is keeping the 23-hour, 56-minute time. Whatever it is, it's moving round with the stars. But it's very hard to tell what it is because it's all jammed into 5 millimeters. So I showed these recordings to Tony and said, what do you think this is and what do we do about it? And Tony rightly observed, well, it's all jammed into 5 millimeters and you can't really see what's happening. We need an enlargement. And with chart recordings, enlargements are easy. You just run the paper faster underneath the pen and everything gets spread out. So, okay, we just switch the pen recorders to high speed. The pen recorder runs out of paper after 20 minutes. And guess who has to live at the observatory day and night putting a fresh roll of paper in every 20 minutes? Not a good idea. Next best idea. The graduate student goes out to the observatory at this time, switches to the high-speed recording, lets it run at high speed till about this time, and switches back to normal. And I did that religiously for a month, and I made high-speed recordings of this stuff, which is ambient receiver noise. And it wasn't that I'd got the time wrong. The thing had disappeared. It had gone. And Tony was livid. Oh, it's a flare star. It's been and gone and done it, and you've missed it. If you haven't experienced being a grad student, you need to know that grad students serve the same purpose as the cat. They're for kicking when things get bad. Finally, one day I said, sod this, I'm skipping going out. By this stage, the thing was transiting at lunchtime. It was a very interesting lecture in Cambridge I wanted to go to. I remember it vividly because of the circumstances and because it was on ageing. Gets more relevant. Next morning I went out to the observatory. It had reappeared after a month's absence, and I'd missed it. I didn't dare leave. I stayed out at the observatory. Fingers hard crossed that after a month's absence it would show 2 days in a row. And this is the recording I got. The bottom trace is man-made, human-made 1 second time pips, which were broadcast in Britain and we put on our records. The upper trace is the signal that came in. And you can see a faint hint of pulses at the left-hand end. Bump, 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 one missing, bump, 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 several missing, back on cue. So even where the pulses went missing, it kept the beat. Didn't miss a beat. Well, it missed a beat, but it didn't lose the beat. And the period is about 1 1/3 seconds. Well, I'd seen nothing like that before. I decided I would break with convention and phone my thesis advisor. He was he was teaching in an undergraduate laboratory, probably dealing with some twit of an undergraduate who thinks his diffraction grating has 1 line per inch, and his twit of a grad student phones up, says, "Tony, you know that funny thing? It's a pulse signal 1 1/3 seconds apart." Oh, well, that settles it. It's man-made. I didn't think it was, but I couldn't marshal the argument quickly enough. But the argument I should have marshalled is, on and off, I've been watching this thing now for several months, and it keeps a 23-hour, 56-minute day. It moves with the stars. Human beings keep a 24-hour day. So if it's Joe Bloggs driving down the road in a badly suppressed car after work, he's getting off work 4 minutes earlier each day, 28 minutes. Tony was interested enough to come out to the observatory next day at the transit time and stand looking over my shoulder. And that was one of the really scary bits of my PhD. This thing's been missing for a month. It was there the day I missed it. It was there yesterday. Will it be there a 3rd day in a row? It was. He saw it with his own eyes, and he established that the spacing of the pulses was the same as on the previous day. But he was still hung up on it's man-made, it's artificial. However, he took away all my records and finally convinced himself that it wasn't local radio interference, that it was moving with the stars. It kept sidereal time. So the next thing is, well, Jocelyn's wired up the radio telescope wrong. So the obvious thing to do is to get another radio telescope to observe it. And we did have on site another radio telescope working at the same frequency. And we spoke to the people using it, Paul and his grad student Robin, and said, let them in on what was going on. And said, would you mind seeing if you can see it? And so a few days later, we all congregated out at the observatory. The thing appeared first in my telescope beam, and we could see it was pulsing nicely. And then we went and stood by Robin's chart recorders, because he too worked with chart recorders. And we stood there. And nothing happened. We calculated it would appear in that telescope's beam about 5 minutes later. And it didn't. Tony and Paul started walking down this long laboratory saying, now what could it be that shows in ours and not yours? Could it be? No, it can't be, but I wonder if, no, that wouldn't work. You think? No, no. And I was padding along behind them, and Robin stayed by his pen recorder. We got down this long, long laboratory, and suddenly there was a shriek, "Here it is!" And we came charging back up again. So another radio telescope with its own receiver also picks it up. But of course, they're both on the same site. They're only a few hundred yards apart. So if there's some funny local interference, they're both going to be equally affected. Meanwhile, we had looked quite carefully at these pulses, and we'd observed that the pulses are short, which means the thing has to be small. But we'd been observing it probably for about a week or 10 days by then, and it was keeping the same period. So it wasn't getting tired. So it's got large energy reserves. So it's big. It's small and it's big. Yippee! You have to sharpen up the questions or the statements slightly. Yep, it's got short pulses or steep pulses, which means it's small. It keeps an accurate pulse period, which means it's got a lot of energy reserves. It's big in the sense of being massive. So it's massive and small. We still couldn't think what that was, but with hindsight, of course, it's abundantly clear. A colleague managed to get a measurement that allowed us to estimate the distance. When a radio signal propagates through space, it gets dispersed, and higher frequencies arrive a little bit before lower frequencies. This is the radio equivalent of a rainbow. And my colleague took two receivers, tuned them to slightly different frequencies, found that the pulse appeared first in the high frequency, blip, 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 blip. And the spacing between blip and blip gives you an estimate of the distance. And he estimated it was about 200 light years away, which puts it beyond the sun and the planets, but way out in our galaxy, not beyond the galaxy. Tony wondered if it really was little green men, aliens signaling to us. And he argued that if it was aliens, they probably lived on a planet which went round their sun. Now, for a moment, pretend you're the observers and I'm a little green person on a planet orbiting my sun. And I'm sending out pulses. And as I walk towards you, the pulses pile up on each other a bit, the spacing between them smaller. And as I walk away from you, the spacing between them is larger. This is what we call Doppler shift. You've probably come across Doppler shift. Have you ever seen a child go, meow? That change in pitch, meow, is Doppler shift. Higher when it's coming towards you, lower when it's going away from you. Same thing here with little green men. So I continued making these observations to look for Doppler shifts. And couldn't find, well, no, it's not true to say we couldn't find any. We found a Doppler shift. But actually, there's a Doppler shift because the Earth is moving around the sun. Because that moves the telescope, or moves the telescope away. So we proved that the Earth went round the sun, but otherwise weren't making a lot of progress. One evening, about 3 weeks into this story, just before Christmas, I went down to Tony's office to ask him something, and rather unusually the door was shut. So I knocked, and Tony said, "Come in." Put my head round the door. "Ah, Jocelyn, come in," and shut the door. So I went in and shut the door. And there was a discussion going on. There was the Martin Ryle, who was the head of the group, the professor. There was Tony, my thesis advisor, and there was another senior radio astronomer who was an editor of one of the journals. And it was a conversation that I think I should have been part of right from the beginning. How do we publish this? We've only got one. It looks absolutely crazy. We've done just about all the tests we can think of. We really ought to publish it and tell the rest of the world. But we'll never get it accepted if there's only one crazy thing. We didn't solve it that evening. I went back for some supper really rather cross. Why do some little green men have to choose my frequency and my radio telescope to signal to Earth? I'd only a few months' money left on my thesis grant, so it was getting serious. Came back in after supper to do some chart analysis. The laboratory got locked at 10 o'clock at night. Grad students did not have keys. You could be locked in for the night or locked out for the night. And doing some of this routine chart analysis from a totally different strip of sky, there was a patch that was really barely usable. It was a problem with a very, very strong radio source low on the northern horizon. And our telescope could see it through the back of the telescope. It was such a strong source. And it really messed up the records. And I got quite used to just abandoning, about 20 inches of chart recording. And I got to that bit at about 5 to 10. Suddenly saw in the middle. Whoa, that looks like... Wow, right. Yes, okay. Out comes the box that covers this strip of sky. Throw out the charts on the floor, roughly line them up. So here's tonight where I think I've seen it. No. It might be in there. It's very weak. No. Ah, I missed that. Oh, and there's another. And they all line up. And that bit of sky is going to be seen by the telescope at 2 o'clock in the morning. I've got to be there. And the janitor's locking up, throw the charts on the desk and run out with the janitor locking the doors behind me. Go out to the observatory at 2 o'clock in the morning. It's the 21st of December. It gets quite cold in Cambridge, not perhaps as cold as it gets here on the 21st of December, but pretty cold. And something in the telescope didn't like cold weather. And it wasn't functioning properly. So I swore at it, I flicked switches, I breathed on it. I got it to work for 5 minutes at full strength. It was the right 5 minutes and the right beam setting, looking at the right bit of sky. And in came pulse, 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 pulse. This time 1 1/4 seconds apart. The first was 1 1/3, but otherwise the same kind of thing. Fantastic. I somehow got a message to Tony and I went off to Ireland. My boyfriend came with me and we announced our engagement. And Tony kept the survey running over the Christmas holidays, which means he put paper in the chart recorders, ink in the ink wells, and piled the charts unanalyzed on my desk. I came back after Christmas sporting this engagement ring. It was really daft. I should not have worn it into the lab. In those days, married women quit work. It was considered shameful if a married woman had to work. It meant he couldn't earn enough to keep them both. But I was terribly proud of that ring. So Tony's in a meeting. It's quite clear what I have to do. I sit down to do some chart analysis, merrily working along. Oh, which one's that? It's not either? Wow. Okay, I'll just finish this piece of chart and then I'll come back and, address this. So move on. What? 2? About 1 meter apart on the same piece of chart? At that point, Tony appears and stands at the end of the desk. Hey, Tony, look. Oh, Happy New Year, Tony. Thank you for keeping the survey running. Look at this. Huh. How many more have you missed? Go back through all your old records. I did. We didn't find any more candidates, and over the next couple of weeks, we confirmed the 3rd and the 4th. And that's good. That's great. We can now publish. So we pushed ahead, we published the first one, and a paper on the 2nd, 3rd, and 4th, shortly following behind. Just a little story for the benefit of those in the audience who know who Fred Hoyle is. Shortly before the paper announcing the first one was published, Tony gave a colloquium in Cambridge, gave it a very titillating title, and everybody came. We'd been fairly cautious about shouting about this because we were really, really worried that it was something with a mundane explanation and we'd look very stupid. So it hadn't become broadly known. Tony did his colloquium. Fred Hoyle was sitting in the front row, and at the end of Tony's speech, Fred said, and I'll imitate his Yorkshire accent, "This is the first I've heard of these things." And we weren't surprised because we'd been fairly careful with what we said. "This is the first I've heard of these things. I don't think it's a white dwarf," which was Tony's favourite model. "I think it's a supernova remnant." Supernova are stars that explode, and the core of the star gets very compressed and becomes known as a neutron star. And we hadn't very seriously considered neutron stars because Tony liked the white dwarf model. Fred, starting from cold, in 45 minutes has hit the right explanation. That man was a fantastic physicist. Really very impressive. There was lots of publicity around it. Typical interview would be Tony and I, and the journalist or the TV or whoever it was would ask Tony about the astrophysical significance of this discovery, which Tony duly gave them. And they then turned to me for what they called the human interest. How tall was I? How many boyfriends did I have? Would I describe my hair as brunette or blonde? No other colours were allowed. And what were my vital statistics? It was nasty. It was horrible. You were a piece of meat. Photographers would say, "Could I undo some buttons, please?" Oh, it was awful. I would have loved to have been very, very rude to them, but I reckoned I'm a grad student. I've not finished my data analysis. I've not written my thesis. I've not got a job. I need references. You're quite vulnerable. So, however, one nice thing was the Daily Telegraph, which is a rather right-wing but otherwise respectable newspaper in Britain, pro-Brexit. It's its science correspondent, Anthony Michaelis, interviewed us and said, "What are you going to call these things?" We'd had a serious discussion about whether in the paper we described them as pulsed radio sources or pulsating radio sources, and opted for pulsating as pulsed might imply an agency, little green men, making it pulsed. But we hadn't thought of a short name. And it was Anthony Michaelis who came up with the name pulsar, by analogy with quasar, which we already have. And these days, as you know, the name has travelled. There's watches called pulsars. Certainly in the UK, there's models of Nissan cars called pulsars. You can sometimes find geraniums called pulsars. Same name. I'm told that in the United States, the watch company tried suing the radio astronomers for use of the name. So, we're going to get serious now. What are these pulsars, other than that they're small and they're massive? We'll start with the video because that's probably already catching your eye. Very small star, spinning about an axis that's vertical in this configuration, and two beams coming out of it. They actually come out from the magnetic poles as opposed to the rotational poles. And if the beam shines in your eye like now, you see a pulse. The other beam misses you, you don't see a pulse. You see the first one again. More static model on the right-hand side. Doesn't actually add a lot, but it shows you more of the magnetic field lines. we still don't fully, well, a lot of us still don't fully understand how the radio beam is made, but it does seem to come from the region above the magnetic poles. They're very small, very dense, neutron-rich, but not pure neutron objects. So they're also called neutron stars, with very strong gravitational fields, very strong electrical and magnetic fields, and rapidly spinning. And I'll unpack all of this in a moment. They're probably formed in the explosion that occurs at the end of the life of a massive star, things at about 10 times the mass of the Sun. They were the core of the star, and in the explosion they got kicked against and compressed. And the main way we see them is as these pulsed radio-emitting objects. If you did what radio astronomers never do, and that's listen to what the radio telescope's picking up, it might sound like this. So these objects are seen primarily in the radio, rarely in the visible, sometimes in X-rays and gamma rays. And we've now got around about 3,000 or pushing 3,000 of them. A few in the visible, about 100 in X-ray, and a surprisingly large number at the high energy gamma rays. Most of them are isolated. Some of them are twinned with another star. One of them is a pair of pulsars and is fantastically useful. They're closely spaced pulsars. They go around very fast. Really, really good for checking out Einstein's theories of relativity. Einstein's theories of gravitation. And Einstein's theories of gravitation check out very nicely, which is interesting. One is in a triple system. That's being used to check out Einstein's principle of equivalence in the strong field. Do objects of different composition fall in the same way under gravity? We haven't got a result on that one yet. There's got to be, the answer's pretty close, whichever way it is, and they've got to pay a lot of attention to the errors and the systematics. So there isn't really an answer on that one yet. And there are a few with planets. And I can give you several good reasons why a pulsar shouldn't have planets, or shouldn't still have planets, but there are a few. And there may be about 100,000 in our galaxy, and similar numbers in similar galaxies, presumably throughout the universe. So a little bit more about how they're formed. I alluded to the fact that a massive star explodes with a catastrophic bang, burst, towards the end of its life. The core of the star gets kicked against and gets compressed. So this has been one of the first and best supernovae explosions we saw. There's a star here picked out with an arrow. You don't need the arrow here. It's dramatically exploded. And just to be absolutely clear, the arrow's added after the photograph's taken. This exploding star was observed by the Chinese in 1054 AD. For a long time, we weren't quite sure why it kept shining so well. We now know there's a pulsar in there, and that's what helps keep it shine. So in a little bit more detail for anybody who's a physics freak, these things have a mass of a few times 10 to the 27 tons. That's a few thousand million tons. So comparable broadly with the mass of our sun. But they're a little ball with a radius of only 10 kilometers. And I don't mean 10 to the power something, I mean 10 kilometers. So you could put one down in Toronto and we'd be fine here, for example. You wouldn't want to put one down on Toronto, would you? Their average density is like the density of the nucleus of the atom. And we believe they're rich in neutrons, hence the name alternative name neutron stars. The density is phenomenal, and to unpack that just a little bit, take a thimble, a sewing thimble, preferably a nice silver one. Take the population of the globe, 7 billion people, jam them into the thimble, one by one. Teenagers love this. And when the thimble is full with the 7 billion people, or 7 point something billion people, it has the same mass as if it were filled with material from one of these stars. They are really dense. And because they're dense, the gravity at the surface is very strong, there are tidal effects, and the physics of the inside is fantastic because they're very condensed matter, very solid state physics. The strong gravity bends light, so if I stand on the surface of one of these stars, I can see over the horizon, probably about 20 or 30 degrees, and without moving I can see about 2/3 of the surface of the star because of the way light bends. The gravity will also redshift light. So if there were little green men on these stars, they'd look like little red men to us. And the gravity also affects clocks. Instead of doing a tick every second, it does a tick every 2 seconds. If I went with the clock to one of these stars, I could take my pulse with it. It would seem perfectly normal. And that's because the gravity has also slowed my heart and my metabolism. It slows everything. There's also a very strong gradient of gravity. Suppose I'm coming in to land on one of these stars, and I'm coming in feet first, because that's the ladylike way to land on a star. And as I get pulled down, the gravity's strong, but the gravity on my feet is perceptibly stronger than the gravity on my head, and it stretches my body long and thin. And actually, worse than that, it starts pulling the body apart. So don't go visit. There's also phenomenal magnetic fields, something like 100 million Tesla. To put that in context, your fridge magnet is about 1/100th of a Tesla. And if you spin a magnetic field, you get a huge voltage drop, probably about 10 billion volts per centimetre, which means, strong though the gravity is, the electromagnetic forces are 100 billion times stronger. So don't take your credit cards when you go. They're very good timekeepers. Once you get 1,000 million tons spinning, it's the devil's own job to make it change its spin, so it just keeps going round. And the typical pulsar is accurate to 1 part in a 10,000 million, which means the typical pulsar's period has increased by about 1 second since the age of the dinosaurs. These things are brilliant clocks. For a time we thought they'd become the best clocks humanity knew. In fact, the US has been working on this since then, and they're no longer quite as good as some of the best human clocks, timekeepers, but they're still very good. And we're using them as clocks dotted throughout the galaxy to test Einstein's theories of relativity. The field is going to get even more exciting. The Chinese are just opening a radio telescope that is 0.5 kilometre across, 500 metres. It's in the south of China, in limestone country. If any of you have seen the telescope in Puerto Rico, it's done in similar country, but of course this is bigger, being Chinese. It's currently being commissioned. I know the chief scientist. He was telling me in August that they had about 70 new pulsars, and he said some very interesting, weird things, but wasn't, of course, going to say more about what those were. Nearer home, in British Columbia, is CHIME, Canada's newest radio telescope. This gives you a good overview of the scenery. Closer up, there's 4 cylinders, and this type of radio telescope is good for pulsar work because it's about got both good sensitivity, lots of area to collect the radio waves, but also good pointing, good beams. So this is just starting operation. I haven't heard anything out of it yet about pulsars. There's one or two other rumours coming out, but not yet on the pulsar front. So I'm sure there's going to be lots of wonderful stuff there. And I'm going to finish this rather crazy canter with some even crazier pulsar records. The centre of a neutron star, the pressure is large. The fastest known pulsar, currently the fastest known, is this one. This is the way we name them, PSR for pulsar. Their right ascension, which is like longitude, and their declination, which is like latitude on the sky. And this is its period in milliseconds, thousandths of a second. And look at the accuracy. And that's 3 at the end is not all experimental uncertainty. The period is actually increasing in the very last decimal place. The audio recording probably won't work, but let's just try. It's going so fast, it whines like your kitchen blender. It's doing about 700 revs per second, and it's an amazing thing. So it's quite staggering that a star can spin that fast and be stable enough that we can measure a period like this in milliseconds. You would not expect pulsars to have planets, but in fact they have discovered planets round one particular pulsar. 3 planets, and now they think there's a little 4th one as well. The way they get these is, if I'm a pulsar and this is a planet, as the planet goes round the pulsar, it tugs the pulsar ever so slightly, and the pulsar moves around a little bit. And you can detect that Doppler shift due to the motion of the pulsar, due to the planet. It gets more complicated when there's several planets, but with time you can disentangle it. The roundest known thing in the universe is the orbit of this particular pulsar. It's round to about 5 microns, which is smaller than the width of one of your hairs, and the orbit is about 500,000 kilometers. So that's round to incredible accuracy. If you know anything of conics and eccentricity, that's the eccentricity. Almost perfectly circular. And finally, if you go somewhere near a pulsar and let something fall onto the surface, it hits the deck travelling at half the speed of light. So strong is the gravity. I find these things truly amazing, and although I keep reciting these facts, I'm still not quite sure I believe it. But I can assure you it is correct physics. The numbers are indeed right. Thank you for your interest.
Wow, thank you. Let's have some questions. So there's a microphone there for those of us here in the theater, and the online questions are also flowing in. So let's start right here in the theater.
Hi. Thank you so much for your talk. That was really fun. I was wondering, you know how things in the sky, in the universe, they fall apart and we get detritus coming to the planet, and I wondered if a neutron star explodes, could it ever separate enough that we would see little pieces of it float to the planet? And if they did, would they maintain that density? And would there be any danger to them falling? And have they discovered any remnants of a neutron star?
The answer to most of your questions is no. No, they haven't seen yet an exploding neutron star, and I would think they're too far away for the detritus to hit us. But there is a related question. These stars are formed by big stars exploding, and it's the core of the big star. Are we in danger from one of these big stars exploding? The nearest big star to us that will explode one day is in the constellation of Orion. It's the one on top left, the reddish one, called Betelgeuse. One day, Betelgeuse will explode. And as well as a sort of fireworks, there's risks from X-rays and things like that from produced in the explosion. It turns out that if there's an explosion within about 25 light years, we need to worry. Betelgeuse is 65 light years, so it's at a reasonably safe distance, and we don't know of any star closer than 25 light years that will explode. Some have in the past, but there aren't any left now within that distance. We'd undoubtedly see them if they did exist because they'd be so bright. So we think we're okay on that score.
Let me quickly do an online question and we'll come back. And I just hit the wrong button. So, hello from Greece. Can you give advice to young people who want to get involved in research? Is there some piece of advice you wish you had listened to when you were a student?
Wow. It is great fun being a research student, but it's several years hard slog. It is the normal way into research. But if people don't feel they can face that or can't fund that, then increasingly online, there are things that people can help with. This is called the Citizen Science Project. It started in Oxford. It started with a research student and his supervisor. The research student had the job of classifying 1 million galaxies. He had photographs of 1 million galaxies, and he had to say, that's a spiral, that's elliptical, da, 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 da. And he worked like the clappers for 1 week and did so many thousand, and then multiplied up and said, you're not going to do 1 million within a studentship. So what they ended up doing was putting all those photographs on the web, providing a short tutorial. This is an elliptical galaxy, this is a spiral galaxy, and inviting the public to do the classification. And the public piled in. And now increasingly you can find on the web, under the general heading of Zooniverse, so instead of universe, it's Zooniverse, under the heading of Zooniverse, a lot of projects that desperately need human intervention. And incidentally, they're not all science ones either. So if anybody's interested in that kind of helping with research, your efforts would be greatly appreciated.
Thank you. In the theater.
Hi. So I'm an undergrad in physics, and one of the big things that I want to do in my master's is physics education research. As someone who's gone through, as a woman, minority, even just a physicist, what do you think are the next steps in the future to encourage more people to be in physics, not just women, but anyone in general?
We're in an English-speaking country. I come from an English-speaking country. The English-speaking countries have a problem that not all countries in the world have. I'm extrapolating from astrophysics, but I think it's fair enough. The English-speaking countries, Australia, US, Canada, UK, all lie below the world average in terms of the percentage of astronomers who are female. Northern European countries like Germany and Netherlands are worse. Better than average are South and Central American countries and the Southern European Catholic countries like France, Spain, Italy. There's actually quite a range around the world in the percentage of women who are astronomers. And this says to me that there's nothing wrong with women's brains. That's not why we have relatively few women in physics. It's not the brains, it's the local culture and the way society is organized. Women can do physics, women do physics and do it well. So we just need to convince the English-speaking world that easy, that's the situation.
I'll work on that.
Let's go inside the theater again.
Hi, thank you so much again. I was just curious about when you were talking about, like, you saw the pulses on the chart paper, but then why did they disappear for, like,
yes,
amounts of time and then come back?
Thank you, and I didn't explain that. The project started with what we called interplanetary scintillation, the twinkling of compact radio sources like quasars. What we inadvertently discovered, along with pulsars, was that there's another kind of scintillation produced in the space between the stars, interstellar scintillation, that also can brighten or fade a pulsar or anything else. But the timescale for that is not fractions of a second, it's weeks. And so these pulsars can disappear for weeks, but they can also be brighter than average for weeks. So you lose some and you win some.
We'll take an online question. So this question, do you still enjoy stargazing? Or does doing astrophysics take some of the joy out of looking up on a clear night sky?
A clear night sky I find very, very impressive. The sad thing is that we've got more and more street lighting, and for those of us who live in urban areas, it's hard to see a good night sky. Typically in Britain, you cannot see the Milky Way from any city in the country. I would guess it's the same here, unless it's a very small city. You have to get out of the town, away from the lights. But if you get out into the countryside, it's magnificent.
Excellent. In the theater.
Speaking of looking at the sky, you said that some of the pulsars were discovered in the visible wavelength range. Mm-hmm. How close would one have to be for us to actually see it blinking?
There's several very interesting stories, particularly concerning the pulsar in the Crab Nebula that I showed you. There's a story way back from 1957 from the McDonald Observatory in Texas. When McDonald gave money for that observatory, he specified that it had to be open to the public one night per month. And this story comes from a gentleman called Elliot Moore, who at that stage was a summer intern in the observatory, having just finished his bachelor's degree. And the telescope, it's a public observing night, the telescope is set on the Crab Nebula, and the rather curious star in the middle of the Crab Nebula that we now know is a pulsar going at 30 times a second. And people stepped up to the telescope and said cool and awesome, or whatever they said in 1957. And a young woman steps up to the telescope and says, "That star's flashing." Now that pulsar is one that flashes in the optical. It's one of very few. She says, "That star's flashing." The night assistant starts to explain to her about scintillation, the way stars twinkle and planets don't. And she stops him and she says, "No, I hold an airplane pilot's license." For God's sake, this is 1957, it's a young woman. "I hold an airplane pilot's license. My job is to fly newly built aircraft from the manufacturer to the customer. I fly at night. There's not much to do in the cockpit. I know about scintillation. That star's flashing." Now, it flashes at 30 times a second. But as some older Canadians may remember, the main power supply here used to be at 30 hertz, 30 times a second. And some of you could see the lights and the television and things flashing. Some people can see 30 hertz. We suspect she saw it. But nobody followed up. The excuse was there wasn't an appropriate bit of equipment. Elliot Moore thinks there was, and there was just an idleness. Always follow anomalies. So, yep, the occasional pulsar you can see flashing, but not many of them, because they're normally very weak.
Thank you.
One more question.
Hi, thanks for the talk. I'm a fan of the Pioneer plaques.
Yes.
As you probably know, there's a pulsar map on there.
Mm-hmm.
I was wondering if you had any comments on that.
Yes, so these are plaques that went on the 2 Voyager satellites, which have now got way beyond the sun and the planets and apparently still going strong. There's some golden discs, and there are these plaques showing some things about humanity. There's a man and a woman with no clothes on, and that caused some consternation in the Midwest. And there's in one corner of the plaque what looks like a sort of star pattern, lines coming out from a point. And the point is the Earth, and the lines indicate the directions of certain pulsars, and there are ticks on the lines that give the pulsar period. So if the aliens who pick up these satellites can decode all this, they can find where Earth is, and they can also find out when this stuff was sent off, because the periods have aged a bit since then. Some people say it's dangerous to tell aliens where we are, but we've been and gone and done it. And actually, ever since we've been broadcasting television and things, the radio waves have been traveling out through space. So there's not a lot we can do to retrieve the situation at this point. But I was rather proud that they put pulsars on those plaques.
Thank you.
Thank you.
Ladies and gentlemen, Dr. Jocelyn Bell Burnell.
Thank you very much.
Neutron stars, and a bit of a mention there of the Large Magellanic Cloud from the Astromofo contest. Now we'll finish off, this goes for about 5 minutes, about the colour of noise. Some of you may have heard of things like white noise and so forth, but there are several other colours as well, and this will explain all about that, and then we'll close for the evening.
So, you've heard of white noise. Did you know there was pink and blue noise, and indeed perhaps green noise and red noise and a whole range of other noises? Where do all those different colours come from, and what is white noise anyway? How can noise have a colour? Yeah, so I can just do it here. There we go. Yeah. Okay, so that's white noise. So that's the sound of a signal which has absolutely no periodicity to it. It's entirely and utterly random. Why do we call it white noise? Well, we call it white noise in analogy with spectrum of light from a rainbow, for example, or any type of spectrum. So all frequencies contribute equally. So just as you have with white light, all colours contribute equally. In this case, all frequencies. What does that mean? Well, you can think of a wave, and a wave varies in time. And so if it's varying with a slow frequency, it's changing on slow time scales, and it's not, very rapid. But then you can also have high frequency waves, which oscillate back and forth very, very quickly. So a difference between a and a that's what I'm talking about. You mix those all together, all those different frequencies, from the very, very slow to the very, very high, and you mix them all together equally, and what you get is white noise. So what you were hearing was a sample of white noise, which has been generated very simply on a computer, which covers frequencies from very, very low, close to 0 hertz, all the way up to about 20 kilohertz, something like that. And it's an equal mixture of all those frequencies. And that's what this is showing us. It's showing us the power associated with each frequency. And so you mix it all up, so all the powers contribute equally, and what you get is white noise. So that's our spectrum for white noise. So just as we have, if you have a pink color or a red color or a blue color in terms of light, it means that certain frequencies are dominating, certain wavelengths, certain frequencies are dominating. If you've got pink noise, then what you have is the lower frequencies, which are moving towards the red end of the spectrum, are contributing more. So if we look at a spectrum for pink noise, did you hear any difference at all?
Was that low? Was that supposed to be lower pitch?
So, well, it's not. That's meant to be pink noise, so it's meant to be different from white noise. Can you hear any difference? Will we play the two back to back and see if you can hear any difference? Can you hear that lower frequency rumble?
Yeah, it's deeper.
It's deeper. And that's what we'd expect, because in this case, when we look at the frequency spectrum, then what we find is instead of it being flat, it tails off. And so what we have is the lower frequencies contribute more than the higher frequencies. So we hear that rumble. And in fact, the 1/f noise, if you listen to it again, sounds rather like rainfall. Listen to it. Imagine being sitting inside and you listen to the rain outside.
You just said 1/f.
Yes, did I just say 1/f? Okay, yeah. So that's how the frequency spectrum goes. So the power in this case goes inversely with the frequency. So as we're going up in frequency, the power is dropping down. So it goes as 1/f. So the white noise has no dependence. So no dependence on frequency, so it's a constant. So it's flat. So, but we can also have blue noise. With 1/f, so it falls off with frequency. So it's inversely dependent on frequency. If we have blue noise, then you probably can guess what it's going to do. But let's have a listen to blue noise first of all. The power last time was proportional to 1/f, so it was falling off with frequency. Now it's proportional to f, so it's growing with frequency. And it's exactly the same. So what we're doing with 1/f is we're weighting it towards the lower frequencies, getting redder, getting pinker. What we're doing now is we're weighting it towards higher frequencies, getting bluer.
When I think of white noise, I think of that fuzz on the TV. What's that?
That's a visual representation of what we're hearing here in terms of exactly the same idea, where we get a great deal of frequencies all contributing together. Once we have all those frequencies contributing, so we don't have a spectrum with a ramp like it on this, where it's a flat spectrum, we call that white noise. In some cases, depending on the equipment you have and depending on the type of setup you have and depending on how your aerial's working, you might have deviations from white noise. But white noise means that you have got to have everything contributing to the same extent. You'll get a lot of websites saying that what you should do is fall asleep with pink noise because it gives you a more sort of harmonious brain rhythm. There seem to be some papers that make suggestions along those lines. I'm not entirely convinced, I've got to admit. I must admit that part of me thinks that what we should do, Brady, is just record a lot of white noise and pink noise and blue noise and send it out there and charge a little bit of money for it. I think we could set up a business fairly quickly.
Phil, I want to hear black noise. You always wear black.
Oh, that's interesting. There is even black noise. There is black noise.
What's black? Surely that's no noise.
That's exactly what it is. Black noise is an absence of any noise at all. But it's even defined. You can find a wiki entry on black noise, which I didn't even realise until very recently.
That's what we should do, sell black noise.
There is that concerto, isn't there? That piece of classical music, or meant to be classical, which is like a time, 4:32 or something, which is just silence, just pure silence. That's what it is. I think it's called John Cage, isn't it?
There's something ironic that, like, you know, heavy metal people wear black, and yet black noise
is silence. No, that's good. Yeah, absolutely.
Just close by looking at some video that was released recently by NASA from their Solar Dynamics Observatory in Earth geosynchronous orbit. This is looking in the extreme ultraviolet, so it's looking at the sun's corona. I've actually removed some dark frames, so if you see some of the images flicker, it's because they're not recording 7x24. Because it's in geosynchronous orbit, on rare occasions the Earth comes in front of it, or the Moon comes in front of it, and blocks the Sun. And sometimes they actually have to take the instruments offline to recalibrate them. So it's not an unbroken record that NASA actually has of the sun's surface, so that comes as a bit of a surprise. And the background music that I've put to it is Gangkar Punsum, which is the name of actually the tallest mountain in the world that's never been climbed and probably won't ever be climbed. So though Everest is higher, this one is actually not quite as high, but is pretty much considered unclimbable. And that'll be in the background. This goes for a couple of minutes. And thank you very much for coming to January's meeting.
What wavelength of light was that in?
That's extreme ultraviolet, so just about 17 nanometers. So to give you an idea, the colour of light that we see at the far end, the red end, you're looking at 600, 700 nanometers. The greens and blues, you're down around the 300, 400 nanometers. So 17 nanometers is very, very short ultraviolet wavelength, so very, very energetic. And when you actually see the auroras, like some of the pictures on the wall here of the auroras, they've come from outbursts from the sun, and you can see some of the outbursts on that image where the field lines, you can actually see the magnetic field lines look like sinews can snap and reconnect, and in those cases it can throw particles out into the solar system, and of course if they head in the direction of Earth, we stand a chance of getting an aurora. Anyway, we'll see you all hopefully next month. Thank you very much.